Now in this lecture we'll answer on two questions. In the first question we'll find out the radius of this circle that is described by triangle ABC. In the second question we'll find out the area of this rectangle ABCD that blocks this circle. We'll start with the first question. In the drawing we have triangle ABC. Side BC equals to 2 units, angle ABC equals to 60 degrees, angle ACB equals to 75 degrees, and our mission is to find out the radius of this circle that is described by triangle ABC. So we start with the first method. In the first method, from point C we will draw perpendicular on AB. I repeat again, from point C we will draw perpendicular on AB. This angle equals to 90 degrees according to our construction. This angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular for point C and AB as point D. And we'll focus on the right triangle, triangle BDC. So I will copy the right triangle BDC in the new page and we'll analyze triangle BDC. Side BC equals to 2 units according to what is given as the question. So this is the right triangle, triangle BDC that I copied from the original drawing. And you know that the sum of the angles in the right triangle BDC must be equal to 180 degrees. So here actually which angles we have in triangle BDC. We have this angle that is equal to 60 degrees plus this angle that is equal to 90 degrees plus this angle, the missing angle that we will define as angle X. So plus angle X. In total the sum of those three angles must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So here 100 degrees plus 60 degrees is 150 degrees plus X equals to 180 degrees. Here we subtract 150 degrees from this equation and we get that the missing angle, angle X, equals to 180 degrees minus 150 degrees, it is equal to 30 degrees. So we found out that the missing angle here, angle x, equals to 30 degrees. Here, this angle x equals to 30 degrees. So in triangle BOC, we continue to focus on in triangle BOC. In triangle BOC, sinus 30 degrees, sinus 30 degrees, equals to BD over BC. Okay, yeah. So it is equal to BD over BC. BC is 2, so we substitute BC by 2. And sinus 30 degrees equals to 1/2, so 1/2 equals to BD over 2. Here we multiply this equation by 2 and we get that BD equals to 2, BD equals to 1. BD equals to 1. So here BD equals to 1. We continue to focus on the right triangle, triangle BDC. The right triangle, triangle BDC. Cosine 30 degrees equals to cosine 30 degrees equals to DC over BC. Okay, cosine 30 degrees equals to DC over BC. So it is equal to DC and BC is 2. So we substitute BC by 2. And cosine 30 degrees is square root of 3 over 2. So square root of 3 over 2 equals to DC over 2. Here we multiply this equation by 2 and we get that DC equals to 2 units. So we found out that here we multiplied this equation by 2 and found out that here DC equals to square root of 3 units. DC equals to square root of 3 units. In the next step, we'll find out the size of angle ACD. What is the size of this angle, angle ACD? From the drawing, it is very easy to see that angle ACD equals to angle ACB minus angle BDC. Again, angle ACD, this angle, it is equal to angle ACB minus angle DCB. Angle ACB equals to 75 degrees minus angle DCB that is equal to 30 degrees. 75 degrees minus 30 degrees equals to 45 degrees. So this angle equals to 45 degrees. Okay, so in the next step we'll focus on triangle ADC. I'll copy triangle ADC in a new page and we'll analyze triangle ADC. Okay, so here So this is the right angle ADC that they copied from the original drawing. The sum of the angles in the right angle ADC is equal to 180 degrees. So which angles we have in the right angle ADC? This angle equals to 90 degrees. This angle equals to 45 degrees. And this is the missing angle. We define the missing angle as x. So plus angle x. In total, the sum of those three angles must be equal to 180 degrees. So 90 degrees plus 45 degrees is 135 degrees, plus x equals to 180 degrees. So here we subtract 135 degrees from this equation, and we get that x equals to 180 degrees minus 135 degrees, it is equal to 45 degrees. Okay? Found out that angle x equals to 45 degrees. So actually, those two angles, they are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. So in front of this angle, we have side AD. In front of this angle, we have side DC. So those two sides that are located in front of equal angles must be also equal to each other. That is to say AD equals to DC. But we have already found out that DC equals to square root of 3 units. So we can write here that DC equals to square root of 3 units. And from this equation, AD equals to DC equals to square root of 3 units. We derive that AD is also equals to square root of 3 units. Here AD is equal to square root of 3 units. So we'll continue to focus on the right triangle ADC. So we copy the right triangle ADC here, and we'll implement the Pythagoras theorem on the right triangle ADC. DC equals to square root of 3 units. We just write down found out that AD equals to square root of 3 units. And the only missing side is AC. So we'll implement the Pythagoras theorem on the right triangle ADC. So here by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AC, therefore the square of the hypotenuse is AC squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AD squared plus DC squared. So according to the Pythagoras theorem, we found out that AC squared equals to AD squared plus DC squared. So here AC squared equals to AD squared. AD equals to square root of 3, therefore AD squared is square root of 3 squared, that is 3, plus DC squared. DC also equals to square root of 3, so square root of 3 squared is 3. So we found out that AC squared equals to 3 plus 3, that is 6. Here we take out of this equation number 1, and we get that AC equals to the square root of 6. Square root of 6. Here we found out that AC equals to the square root of 6 units. So now we know the lengths of all the sides of triangle ABC, and actually we have a special formula for the radius of any circle that is described by a triangle. According to the new formula, the radius of this circle that is described by a triangle ABC equals to, here, R equals to the area of the triangle that blocks the circle, in this case is triangle ABC, over S, and S is the semi-perimeter of triangle, in this case is triangle ABC, or the semi-perimeter of the triangle that blocks the circle. And the definition of a semi-perimeter is the perimeter over 2. The perimeter is the sum of the side lengths of the triangle, and when we divide the perimeter by 2, we get the semi-perimeter. Here, the length of AB is A, the length of AC is B, and the length of BC is C. So the perimeter is A plus B plus C, and when we divide the perimeter by 2, we get the semi-perimeter, that is S. So we just have to find out the area of triangle ABC, and then we find out the semi-perimeter of triangle ABC. We divide each by the other, we divide the two quantities by each other, and we get the radius of this circle, that is the radius actually of this circle that is blocked by triangle ABC. Okay, so here you can write down that the radius of this circle, according to the formula that I presented to you, is equal to the area of triangle ABC over the semi-perimeter of this triangle. Okay, use this formula in order to find out the radius of this circle that is described by triangle ABC. So here, first of all, we find out the area of triangle ABC. The area of triangle ABC is equal to the base of the triangle times the height to the base over 2. So here, the area of triangle ABC is equal to the base we'll choose the base of triangle ABC as AB, and the height to the base AB is also of course DC, because it creates 90 degrees with the base. So AB times DC over 2. So the area of triangle ABC equals to the base times the height over 2. So the area of triangle ABC is equal to AB. AB equals to 1 plus square root of 3. So we substitute AB by 1 plus square root of 3 times the height, that is DC. DC is equal to square root of 3 units, all divided by 2. Here we will open the brackets on this side of the equation, and we get that the area of triangle ABC, we get that the area of triangle ABC is equal to 1 times square root of 3 is square root of 3, and square root of 3 times square root of 3 is 3, all divided by 2. Okay, here square root of 3 is 1.732 plus 3 divided by 2. 1.732 plus 3 is 4.732 over 2. So we actually found out that the area of triangle ABC equals to 2.366 square units. Check if I'm not wrong. Okay, it is equal to 2.366 square units. In the next step, we find out the semi-perimeter of triangle ABC. S equals to the sum of the lengths of its sides over 2. So it is AB plus AC plus BC over 2. Okay, the semi-perimeter is AB plus AC plus BC over 2. AB is equal to 1 plus square root of 3 units plus AC is equal to square root of 6 units plus BC that is equal to 2. So in conclusion, we found out that the semi-perimeter of triangle ABC equals to 1 plus 2 is 3, 3 plus square root of 6 plus square root of 3 over 2. That is equal to 4.59 units. Okay. I'll check again. Square root of 6 plus square root of 3 plus 3 over 2. No, it is actually equals to 3.59 units. 3.59 units. And the radius of this semicircle that is inscribed by triangle ABC will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC. The area of triangle ABC is equal to 2.366 square units, and just right now found out that the semi-perimeter of triangle ABC equals to 3.59 units, and we divide those two numbers by each other and we get that the R equals to 0.6589 units. Okay. The radius of this circle that is described by triangle ABC equals to 0.6589 units. So we finished with the first method. In the next step, I present to you the second method. In the second method, we define the center of this circle as point O. We join points O and C together by a straight line. We join points O and B together by a straight line. We define the point of tendency of tangent BC with this circle as point D. and we join points O and D together by a straight line. According to rule number 1, so point O is the center of the circle. Point D is the point of the circle itself, therefore OD is the radius of this circle. We define the radius of this circle as R. We have here the radius OD that is 1 to the point of tendency, and therefore, according to rule number 1, BC will be perpendicular to the radius OD, that is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. In the next step, we define the point of tendency of tangent AB with this circle as point E. We join points O and D together by a straight line. Point O is the center of the circle. Point E is the point of the circle itself, therefore OE is the radius of the circle that is equal to R according to our definition. And also we have here rule number 1. We have the radius OE that is drawn to the point of tendency, that is to say it is drawn to point E. That is the point of tendency of tangent AB with this circle. Whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius EO. So if AB is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Likewise, we will define the point of tendency of tangent AC with this circle as point F, and then we join points O and F together by a straight line. Again, point O is the center of the circle, point F is the point of the circle itself, therefore OF is the radius of the circle that is equal to R. And actually, we have here also rule number 2 that says that the lengths of two tangents from a common external point to a circle are equal. From point P, we have two tangents to the circle, tangent PA and tangent PB, and according to rule number 2, they are equal to each other in their lengths. That is to say, PA equals to PB. We can implement rule number 2 in our drawing, because in our drawing we have the common external point, point B. From the common external point, point B, we have two tangents to this circle. We have tangent BE and tangent BD, and according to rule number 2, they must be equal to each other. That is to say, BD equals to EB according to rule number 2. Likewise, for the common external point, point C, we have two tangents to this circle, tangent CD and tangent CF. And according to rule number 2, they are equal to each other. That is to say, CF is equal to DC. So, in the next step, we'll prove that the green triangle, triangle OBD, is similar to the orange triangle, triangle EOB, and are similar. It's congruent to the right triangle, the green right triangle, triangle OBD is congruent to the orange triangle, triangle EBO, and they're congruent to each other according to side rule. So we prove that those two right triangles congruent to each other. So here we have triangle, the green triangle is triangle BOD, and we have also triangle the orange triangle is triangle EBO. So why the green triangle is congruent to the orange triangle? First of all, we just right now prove that side BD equals to side BE according to rule number 2. BD equals to BE according to rule number 2. Repeat again. Side BD in the green triangle is equal to side BE in the orange triangle according to rule number 2. In addition, we have here side OD in the green triangle is equal to side EO in the orange triangle. They are both equal to R, therefore they are equal to each other. Here, OD is equal to OE. They are equal to each other because both of them are the radii of the circle. And finally, we have side BO, that is a common side that belongs to both triangles. So BO equals to BO as a common side that belongs to both triangles. So actually, we proved that the green triangle BOD is congruent to the orange triangle EOB according to side rule. Repeat again. The green triangle BOD congruent to the orange triangle EOB according to side rule. From the fact that the two triangles congruent to each other, we derive that those two angles are equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding angles must be also equal to each other. That is to say here, we derive that this angle, that is actually angle DBO, is equal to this angle, that is actually angle OBE. Okay. Those two angles are equal to each other. So if we define angle DBO as alpha, if angle DBO equals to alpha according to our definition, then from this equation we derive that angle EBO or OBE is also equals to alpha. Angle OBE is also equals to alpha. So actually, both those two angles are equal to alpha. Okay, so we can write down that alpha plus alpha equals to 60 degrees. It is given as the question. So if alpha plus alpha equals to 60 degrees, it means that 2 alpha equals to 60 degrees. Here we divide this equation by 2 and we get that alpha equals to 30 degrees. Okay, we found out that alpha equals to 30 degrees. So this is angle alpha, that is equal to 30 degrees. And this is also angle alpha, this is also equal to 30 degrees. In the next step, we repeat on the same process on those two triangles. Actually, we prove that the orange triangle DOC, that the yellow triangle DOC, this triangle is congruent to the pink triangle OFC. So why the yellow triangle congruent to the pink triangle? So I write it down, triangle DOC and the pink triangle OFC congruent to each other. So all those two triangles congruent to each other. First of all, we already found out that those two sides are equal to each other according to rule number 2. So side DC is equal to side FC according to rule number 2. In addition, those two sides are also equal to each other. Side OD equal to side OF because they are both the radii of the circle that is equal to R. Repeat again. Side OD equals to side OF. They are both the radii of the circle, therefore they are equal to each other. And finally, side OC is the current side that belongs to both triangles. Therefore, side OC equals to itself as the current side that belongs to both triangles. So we actually found out that those two triangles can go into each other according to side rule. So the yellow triangle DOC congruent to the pink triangle FCO according to side rule. Okay. The yellow triangle congruent to the pink triangle according to side rule. And from the fact that those two triangles can go into each other, we will derive that those two angles are equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. The yellow triangle congruent to the pink triangle, therefore those two corresponding angles must be also equal to each other. So I can write down that this angle that is actually angle DCO is equal to this angle that is actually angle OCF. So if we define this angle DCO as theta, then from this equation theta equals to DCO equals to OCF, we derive that angle OCF is also equals to theta. Therefore, both those two angles are equal to theta. And according to what is given as the equation, the sum of those two angles is equal to 75 degrees. So theta plus theta equals to 75 degrees, according to what is given as the equation. So here theta plus theta is 2 theta. That is equal to 75 degrees. We divide this equation by 2. And we get that theta equals to 75 over 2 is 37.5 degrees. So theta equals to 37.5 degrees. Here, this angle theta equals to 37.5 degrees. And this is also angle theta, that is also equal to 37.5 degrees. In the next step, we focus on the green triangle, triangle ODB. In the green triangle, triangle ODB, tangents 30 degrees. Equals to OD over BD. Okay. Repeat again. In the green, right triangle, triangle ODB, tangents 30 degrees equals to OD over BD. Here, OD equals to R, so we substitute OD by R over BD. So in conclusion, found out that tangents 30 degrees equals to R over BD. Here, we will multiply this equation R over BD. Here, we will multiply this equation by BD and then we divide it by tangents 30 degrees and we get that BD is equal to R over tangents 30 degrees. In the next step, we'll focus on the yellow triangle, triangle ODC. In the yellow triangle, triangle ODC, tangents 37.5 degrees. Is equal to OD over DC. OD over DC. Repeat again. In the yellow triangle, triangle ODC, tangents 35.5 degrees equals to OD over DC. OD equals to R, so we substitute OD by R over DC. So here we will multiply this equation by DC and then we divide it by tangents 37.5 degrees and we get that DC is equal to R over tangents 37.5 degrees. Okay. So we found out the values of DC and BD. From the drawing, it is very easy to see that BC equals to BD plus DC. Repeat again, BC equals to BD plus DC. So BC is equal to BD and is equals to BD plus DC. So BD is equal to R over tangent 30 degrees plus DC. We already found out that DC equals to R over tangent 37.5 degrees. So here we take R as a common factor from those two expressions, and we get that BC is equal to R is a common factor. What is left for this expression of the we R as a common factor? What is left? It is actually R over tangent 30 degrees plus what is left from this expression after we took R as a common factor from it. What is left is actually R over tangent 37.5 degrees. So here PC is equal to R. Here we calculate the values of those two expressions, and then we will add them together and we get very easy the radius, because we know that BC is equal to 2 units. Okay, so we calculate the value of 1 over tangent 30 degrees. Here we have tangent 30 degrees one over tangent 30 degrees is 1.732 units plus 1 over tangent 37.5 degrees is equal to 1.303, and here we'll add the two numbers together. So find out that the sum of those two numbers is 3.035 times R equals to 2. So here we get that R, we divide this equation by 3.035 and we get that R equals to 2 over 3.035. So we found out that R equals to 0.6589 units. Okay, found out that R equals to 0.6589 units. So in both methods, we arrive to the same results. The radius of this circle equals to 0.6589 units. We finish with the first question. In the next step, I will present to you the second question, and we will solve the second question in two different methods. So, in the drawing, we have rectangle ABCD. Inside rectangle ABCD, we have a circle that is described by the rectangle. Chord PS or SP equals to 6 units in its length. Line segment QS equals to 5 units in its length. And our mission is to find out the area of this rectangle ABCD. Okay, so we start with the first method. In the first method, we define the center of this circle as point O. Here, point O is the center of this circle. In the next step, we know that all the angles inside the rectangle are right angles, so those angles are all right angles. We define side AB as A, and we'll define the width BC as B. And here it is very easy to prove that BC is the diameter of the circle, so BC is the diameter of the circle. We join points O and P together by a straight line. Point O is the center of the circle. Point P is the point of the circle itself, therefore OP is the radius of the circle. We define the radius as R, therefore OP equals to R. P is the point of tendency of tangent BC with the circle, so we write it down that P is the point of tendency of tangent BC with the circle. And we have the radius OP that is drawn to the point of tendency, that is to say to point P, therefore here tangent BC will be perpendicular to the radius PO. So if BC is perpendicular to PO, according to rule number 1, this angle equals to 90 degrees and this angle equals to 90 degrees, according to rule number 1, of course. Here, we will define the point of tendency of tangent DC with this circle as point F. We join points O and F together by a straight line. Point O is the center of the circle. Point F is the point of the circle itself, therefore OF is the radius of this circle that is equal to R according to our definition. Here again, according to rule number 1, because of the fact that the radius OF it is 1 to the point F, that is the point of tendency, of tangent DC with this circle. Therefore, tangent DC will be perpendicular to the radius F4. So if DC is perpendicular to F4, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So actually, we created here quadrilateral OPFC. Inside quadrilateral OPFC, we have 1, 2, 3 right angles. And because of the fact that we have 3 right angles, the fourth angle must be equal also to 90 degrees in order to complete the sum of the angles inside quadrilateral OPFC to 360 degrees. This angle must be equal to 90 degrees. Okay. And here also we have rule number 4. According to rule number 4, the perpendicular from the center of the circle to a chord bisects the chord. Here, from the center of this circle, that is point O, we draw the perpendicular OM on chord CD, and according to rule number 4, the perpendicular OM bisects chord CD. That is to say, it divides it to 2 equal parts. That is to say, CM equals to MD. Okay, CM equals to MD according to rule number 4. We'll implement rule number 4 in our drawing. From the center of this circle, that is point O, we will draw perpendicular on chord SP. From the center of the circle, that is point O, we will draw perpendicular on chord SP. On chord SP. So here, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the construction. We define the touching point of the perpendicular from point O and chord FC, SM, and according to rule number 4, the perpendicular OM bisects chord SP. That is to say, SM equals to MP. SM equals to MP. So if SM equals to X, then MP will be also equal to X. According to rule number 4. So SM plus MP is X plus X, and X plus X is SP. So we can write down that X plus X equals to SP. X plus X equals to the length of chord SP. X plus X is 2X, and 2X equals to SP. But it is given us the equation that SP equals to 6 units. So found out from this equation 2X equals to SP equals to 6. We derive that 2X equals to 6. We divide this equation by 2, and we get that X equals to 3 units. So here X equals to 3 units. X equals to 3 units, and here X, that is actually MP, is also equals to 3 units. Okay. Here OP is the radius of this circle that is equal to R according to our definition. But we have already found out that the diameter of this circle is equals to B. So if the diameter equals to B, then the radius must be equal to half of it. That is to say, the radius R will be equal to B over 2. The radius R equals to B over 2. That is to say, it is equal to half of the diameter. Okay. In the next step, from point Q, this point we draw perpendicular on BC. Repeat again, from point Q, we draw perpendicular on BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and BC as point L. We define the intersection point between QL and the radius OF as H. So actually, we created here by this construction quadrilateral OP edge L. Again, we have here quadrilateral OP edge L. Inside quadrilateral OP edge L, we have 1, 2, 3 right angles. So therefore, the fourth angle must be also equal to 90 degrees. Okay, the fourth angle must be also equal to 90 degrees in order to complete the sum of the angles in this quadrilateral to 360 degrees. This angle must be equal to 90 degrees. So inside quadrilateral OPHL, we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral OPHL as a rectangle. Quadrilateral OPHL is a rectangle. Why? Because it has 4 right angles. Okay. Repeat again, quadrilateral OPHL is a rectangle. But we also know that the opposite sides of a rectangle are parallel to each other. So in rectangle OPHL, we know that side OP is parallel to side edge L. OP is parallel to edge L according to the rule that the opposite sides of a rectangle are parallel to each other. Okay. But here we know that edge L is part of the perpendicular QL. Edge L is part of QL. And QL is perpendicular. Here QL is perpendicular. Is a perpendicular that is perpendicular to BC. So QL as a perpendicular, it is absolutely a straight line. So we can write here that QL as a perpendicular is a straight line. And edge L is part of the straight line QL. Repeat again, edge L is part of the straight line QL. And edge L is parallel to OP. So part of the straight line edge L, part of the straight line QL is parallel to OP. And if a part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to that straight line. Okay? Therefore, we can conclude from it that QL must be also parallel to OP. QL must be also parallel to OP because part of the straight line QL is parallel to OP. So if part of the straight line is parallel to another straight line, then the straight line, the And the entire straight line must be also parallel to the other straight line. Therefore, QL, it is parallel to OP. Okay, and here we have actually rule number 9 here, and according to rule number 9, alternating angles between parallel lines are equal to each other. Here the straight line A is parallel to the straight line B, and here actually we have 4 pairs of alternating angles. Here the angle 3 is equal to angle 5 because those two angles, they are defined as alternating angles and they are located between the parallel lines A and B, therefore they are equal to each other. The same rule is relevant to angles 4 and 6. The same rule is relevant to angles 1 and 7, and the same rule is relevant to angles 2 and 8. They are also equal to each other according to rule number 9. Okay? So here we can implement rule number 9 in our drawing. We know that this QP is parallel to QL. Here QP is parallel to QL, and those two angles that are defined as alternating angles, they are located between the parallel lines OP and QL, therefore they are equal to each other according to rule number 9. So here angle LQP, this angle is equal to this angle that is actually angle QPO. QPO. And they are equal to each other according to rule number 9. There are two alternating angles that are located between the parallel lines OP and QL, therefore they are equal to each other. So if we define angle LQP as theta, this angle equals to theta according to our definition. Then from this equation theta equals to LQP equals to QPO, we derive that angle QPO is also equals to theta. Angle QPO is also equals to theta. So this angle is also equals to theta. In the next step, we'll focus on quadrilateral QDCL. Inside quadrilateral QDCL, we have 1, 2, 3 right angles. And therefore, the fourth angle must be also equal to 90 degrees in order to complete the sum of the angles in quadrilateral QLDC to 360 degrees. This angle must be equal to 90 degrees. So inside quadrilateral QLDC, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral QLDC as a rectangle. Why? Because it has 4 right angles. Quadrilateral QLDC is a rectangle. Okay? Quadrilateral QLDC is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say side QL must be equal to the opposite side DC. QL equals to DC. In rectangle QL DC, QL equals to DC, according to the rule that the opposite sides of the rectangle are equal to each other. But here, we know that ABCD is a rectangle, and the opposite sides of rectangle ABCD also equal to each other. That is to say, side DC equals to the opposite side AB. In rectangle ABCD, side DC equals to the opposite side AB. And for this equation, QL equals to DC equals to AB, we will derive that QL is also equals to AB. QL is also equals to AB. Okay, QL equals to AB. But according to our definition, AB equals to A. Here AB equals to A. And from this equation, QL equals to AB equals to A, we will derive that QL is also equals to A. QL is also equals to A. Here we found out that QL equals to A. So, in the next step, we'll focus on the right green triangle OMP. So, I will copy triangle OMP in the new page and we'll analyze triangle OMP. Angle OMP equals to 90 degrees. It is a right angle according to our construction. The hypotenuse OP is equal to B over 2. And this angle equals to theta. So actually, this is the right angle OMP that I copied from the original drawing. In the right angle triangle OMP, what is the value of cosine theta? Cosine theta equals to MP over OP. Cosine theta equals to MP over OP. So I'll write it down. Here cosine theta equals to MP over OP. MP equals to 3 units and OP equals to B over 2. So here we'll move 2 to the numerator and B to the denominator. Here 2 times 3 is 6 over B is in the denominator. So in conclusion, we found out that according to equation number 1, cosine theta equals to 6 over B. Okay. In the next step, we'll focus on the right big triangle, triangle QPL. In the right big triangle, triangle QPL, this right big triangle, QPL, what is the value of cosine theta? Cosine theta is equal to here cosine theta equals to QL over QP. I repeat again, in the right big triangle, triangle QPL, cosine theta equals to QL over QP. So here, QL, what is the value of QL? QL equals to A according to our definition, according to what we have already found out. And QP, what is the value of QP? From the drawing it is very easy to see that QP equals to 5 plus SP, that is actually 6. 5 plus 6 is 11. So QP equals to 11. So in conclusion, we found out that according to equation number 2, cosine theta equals to A over 11. Okay. So we actually have two different expressions for cosine theta. Therefore, we create equation number 3 that states that cosine theta, according to equation number 1, must be equal to cosine theta according to equation number 2. Okay? So here, cosine theta according to equation number 1 is equal to 6 over b, and it must be equal to cosine theta according to equation number 2, that is equal to A over 11. So here we will cross multiply this equation, equation number 3, and we get that according to equation number 3, A times B equals to 6 times 11 is 66. So we found out that A times B equals to 66. And actually, the area that we are looking for, that is the area of this rectangle ABCD, it is equal to, that is the formula for the area of any rectangle. The area of any rectangle is equal to the length of the rectangle times the width. And the length of rectangle ABCD is AB times the width is BC. But according to our definition, AB equals to A and BC equals to B, so we found out that the area of triangle ABCD equals to AB, and we just right now found out that AB equals to 66. In conclusion, we found out that the area of rectangle ABCD, it is equal to 66 square units. Okay. We finished with the first method. Here the area of this triangle ABCD equals to 66 square units. We finished with the first method. In the next step, I will present to you how to find out the area of this rectangle ABCD using the second method. According to the second method, In the second method, we define the center of this circle as point O. All the angles inside the rectangle are right angles, so this angle equals to 90 degrees. This angle also equals to 90 degrees. This angle equals to 90 degrees. And finally, this angle, it is also a right angle, it is equal to 90 degrees. We'll define the AB, the length of AB as A, as we did in the first method, and the length of the width BC as B. And as I already mentioned in the first method, it's very easy to prove that BC is the diameter of this circle, so I write it down. So here we join points O and P together by a straight line. Point O is the center of the circle. Point P is the point of the circle itself. Therefore, P is the radius of the circle. So we define the radius of this circle as R. And there, the diameter of the circle equals to B. Therefore, the radius must be equal to half of it. That is to say, the radius must be equal to B over 2. So here we have the radius of P that is drawn to the point of tendency, that is to say it is drawn to point P, that is the point of tendency of tangent BC with this circle, and whenever radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius PO. That is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. In the next step, we will extend the radius PO until it intersects with AD. And we will define the intersection point of the extended PO and AD as F. Okay, so here we created actually quadrilateral FPCD or PDC FDCP. Inside quadrilateral FDCP we have 1, 2, 3 right angles. Again, inside this quadrilateral FDCP we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees in order to complete the sum of the angles inside quadrilateral FDCP to 360 degrees. This angle must be equal to 90 degrees. Likewise, according to the same rule, inside quadrilateral ABPF we have 1, 2, 3 right angles. Therefore, the fourth angle, that's actually this angle, AFP, must be also equal to 90 degrees for the same reason. Okay. We define the touching point of chord of the chord, this chord with the circle as point S. We'll join point, we'll define it as point H. We define this point H. In the next step, we join points and edge and S together by a straight line. What is the definition of HP? What is the definition of chord HP? First of all, it is a chord, okay? But what is the other definition of chord HP? Chord HP passes through the center of the circle, that is point O, and any chord that passes through the center of the circle must be the diameter of the circle. Therefore, HP is the diameter of the circle because it passes through the center of the circle. HP is the diameter of the circle, but we already found out the diameter of this circle equals to B. So the diameter equals to B. Okay, in the next step, so we join points N and S together, and in this way we created actually peripheral angle edge SP. Peripheral angle, this peripheral angle edge SP rests on HP, and HP is the diameter of the circle. That is to say, peripheral angle edge SP rests on the diameter of the circle. And we have actually rule number 5 that relates to peripheral angle that rests on the diameter of the circle. According to rule number 5, any peripheral angle that rests on the diameter of the circle, of course, must be equal to 90 degrees. So here we have peripheral angle AMB, and this peripheral angle rests on AB, that is the diameter of the circle. And therefore, peripheral angle AMB, according to this rule number 5, must be equal to 90 degrees, because any peripheral angle that rests on the diameter of the circle equals to 90 degrees. So we actually can implement rule number 5 in our drawing. Why? Because in our drawing we have peripheral angle HSP that rests on HP, that is the diameter of the circle. Therefore, according to rule number 5, it must be equal to 90 degrees. Okay. So we will define angle SPH as theta. We focus on triangle HSP. The right triangle HSP. The right triangle HSP, this angle equals to theta. This angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in this triangle HSP to 180 degrees. This angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in any triangle. Exactly for the same reason, here we have the right big triangle, triangle QFP. This angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta, exactly for the same reason. In the next step, but before that, we have here, we have already proved that quadrilateral ABFP, this quadrilateral is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. According to our definition, AB equals to A. And the opposite sides of rectangle, this rectangle ABFP, are equal to each other. That is to say, side AB must be equal to the opposite side FP. AB is equal to FP, according to the rule that I mentioned. But AB equals to A. Therefore, AFP that is equal to AB must be also equal to A. Okay, AB equals to A. According to the rule that the opposite sides of a rectangle are equal to each other. Okay. Now we will prove that the right green small triangle edges P is similar to the right big triangle QFP. So why those two triangles are similar to each other? So I write it down. We will prove that the big triangle QFP is similar to the small green triangle edges P. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So here, angle QFP is equal to this angle that is actually angle edge SP. So here, angle QFP in the big right triangle equals to angle HSP in the green right triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, we have those two angles that they are both equal to 90 degrees minus theta, therefore they are equal to each other. Here, angle FQP, this angle, it is equal to this angle that is actually angle PHS. I repeat again, angle FQP in the big right triangle is equal to angle PHS in the green right small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. And finally, this angle theta, is a common angle that belongs to both triangles. Therefore, we can write out that this angle equals to itself. Or in other words, we can also express angle theta in two different ways, or two different names. Okay? Angle theta is equal to angle FPQ, and it is also, you can also say that angle theta is also equal to angle HPS. So here, this line expresses the fact that angle theta equals to itself, but we called angle theta two different names. Okay? So finally, we actually proved that the big triangle QFP is actually triangle QFP is similar, this is the sign of similar, to the right small green triangle edges P, according to angle similarity rule. Okay, and from the fact that those two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that FP, the side of the big right triangle, FP over SP, the side of the small green right triangle, is equal to QP over PH or HP. Repeat again. Because of the fact that the small green triangles can point to the right big triangle, can conclude that FP over SP equals to QP over HP. So here FP, the value of FP equals to A, according to what we have already found out. So we'll substitute FP by A over HP over SP. SP equals to 6 units according to what is given as the question. So we substitute SP by 6, and it is equal to QP. Here, QP, the hypotenuse QP equals to 6 plus 5 or 5 plus 6. It's very easy to see from the drawing that the hypotenuse QP equals to 5 plus 6, that is 11. So we substitute QP by 11 over HP. What is the value of HP? As I already mentioned before, HP is the diameter of this circle, that is equal to B. So we substitute HP by B. So according to equation number 1, we found out that A over 6 equals to 11 over B. Here we'll cross multiply this equation number 1, and we'll get that A times B equals to 6 times 11 is 66. So we found out that AB equals to 66, and the area of rectangle ABCD equals to the length of rectangle ABCD, that is AB, times the width of rectangle ABCD, that is actually BC. So the length times the width is the area of a rectangle, and especially of rectangle ABCD. But according to our definition, AB equals to A and BC equals to B. So we substitute AB by A and BC by B, and we get that the area of rectangle ABCD equals to A times B. And we just right now found out that A times B is 66. So in conclusion, we found out that the area of rectangle ABCD is equal to 66 square units. Okay, so in both methods we arrive to the same result, that the area of this rectangle ABCD that blocks the circle, it is equal to 66 square units. So in the next step, I'll summarize the lecture. We'll start with the first question, of course. So in the drawing, we have triangle ABC. And triangle ABC blocks the circle, or the circle is inscribed by triangle ABC. we know that B side BC equals to 2 units in its length, angle ABC equals to 60 degrees, angle ACB equals to 75 degrees, and our mission is to find out the radius of this circle that is described by triangle ABC. So in the first method we did a construction. From point C we drew perpendicular on AB. Again, from point C we draw perpendicular on AB. Then this way we create a triangle CDB. I copied triangle CDB in the new page and analyze triangle CBD. So this angle equals to 90 degrees according to our construction. This angle equals to 60 degrees according to what is given us in the question. And BC equals to 2 units according to what is given us in the question. We know that the sum of the angles in any triangle is 180 degrees, therefore the sum of the angles in triangle CBD is 180 degrees. So which angles we have here? This angle equals to 60 degrees, plus this angle that is equal to 90 degrees, plus this angle that is the missing angle that is angle X. In total they must be equal to 180 degrees. Here we subtracted, here 60 degrees plus 90 degrees is 150 degrees, so 150 degrees plus X equals to 180 degrees. Here we subtracted 180 degrees from this equation and we found out that the missing angle, angle X equals to 180 degrees minus 150 degrees, it is equal to 30 degrees. So this angle equals to 30 degrees. You can write down in the drawing that this angle equals to 30 degrees. Then we continue to focus on the right triangle BDC. In the right triangle BDC, it is very easy to see that sinus of 30 degrees equals to BD over BC. Sinus 30 degrees equals to BD over BC. That is to say, sinus 30 degrees equals to BD over BC, but BC is 2, so we substitute BC by 2 and found out that sinus 30 degrees equals to BD over 2. Sinus 30 degrees is 1/2, so we substitute sinus 30 degrees by 1/2. And in conclusion, we found out that 1/2 equals to BD over 2. We multiplied this equation by 2 and found out that BD equals to 1. Here, this line segment BD or side C by D equals to 1 unit. Okay, then we continue to focus on the right triangle ABD. In the right triangle ABD, it is very easy to see from the drawing that cosine theta equals to DC over BC. Again, cosine theta equals to DC over BC. That is to say, cosine 30 degrees. Cosine 30 degrees equals to DC over BC. So here, so cosine 30 degrees equals to DC over BC, but BC is 2, so we substitute BC by 2. So in conclusion, found out that cosine 30 degrees equals to DC over 2. Cosine 30 degrees is square root of 3 over 2, so we substitute cosine 30 degrees by square root of 3 over 2 and found out that square root of 3 over 2 equals to DC over 2. We multiplied this equation by 2 and found out that DC equals to square root of 3 units. Here, DC equals to square root of 3 units. Then we calculated the size of this angle. We know that angle ACB equals to 75 degrees. Angle DCB equals to 30 degrees. Therefore, this angle must be equal to angle ACB minus angle DCB. That is to say, this angle must be equal to 75 degrees minus 30 degrees, that is 45 degrees. Then I copied the right triangle this ACD in the new page and we analyze triangle ADC. Okay. This is triangle ADC that I copied from the original drawing. So angle ACD, this angle equals to 45 degrees, this angle equals to 90 degrees, and this is the missing angle, and the sum of the angles in triangle ADC is 180 degrees, that is to say 90 degrees plus 45 degrees plus the missing angle X. In total they must be equal to 180 degrees. 90 degrees plus 45 degrees is 135 degrees, plus X must be equal to 180 degrees. We subtracted 135 degrees from this equation and found out that the missing angle, angle x, equals to 180 degrees minus 135 degrees, it is 45 degrees. So here, this angle equals to 45 degrees. So those two angles are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, they are equal sides. So in front of this angle, we have side DC. In front of this angle, we have side AD. And those two sides that are located in front of equal angles must be equal to each other. That is to say, AD must be equal to DC. But we have already found out that DC equals to square root of 3 units. Here, DC equals to square root of 3 units. So from this equation, AD equals to DC equals to square root of 3 units, we will derive that AD is also equals to square root of 3 units. Here, AD is also equals to square root of 3 units. So here we can write down that AD equals to square root of 3 units. Then I copied triangle ADC here and we implemented the Pythagoras theorem on this triangle, triangle ADC. In this triangle, that is actually triangle ADC, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AC, therefore the square of the hypotenuse is AC square, it must be equal to DC square plus AD square, or AD square plus DC square. So AC square is equal to AD square to 3, so AD square is equal to 3 square, that is 3, plus DC square, DC is equal to 3, so therefore DC square is equal to 3 square, that is also 3. So in conclusion, I found out that AC square equals to 3 plus 3, that is 6. We took the root of this equation, equation number 1, and found out that AC equals to the square root of 6 units. Okay, AC equals to the square root of 6 units. And we actually found out all the sides of triangle ABC. Therefore, we can actually find out the radius of this circle that is described by triangle ABC by a special formula that states that the radius of the circle that is described by triangle ABC equals to the area of triangle ABC over the semi-perimeter of triangle ABC, over the semi-perimeter of the triangle that blocks the circle. And the semi-perimeter of any triangle is the perimeter over 2. The perimeter is the sum of the side lengths of the triangle, and if we divide the perimeter by 2, we get the semi-perimeter. So according to this formula, we have to find out the area of triangle ABC. The area of triangle ABC is equal to the area of any triangle that is the base times the height of the base over 2. We choose the base as AB, therefore the height to the base is CD. AB is the base, CD is the height to the base, over 2 is the area of this triangle, triangle ABC. AB equals to 1 plus square root of 3, DC equals to square root of 3. So in conclusion, the area of triangle ABC is 1 plus square root of 3 times square root of 3 over 2. We open the brackets here and found out that ABC equals to square root of 3 plus 3 over 2, and found out that the area of triangle ABC equals to 2.366 square units, and as the semi-perimeter of triangle ABC equals to the sum of its sides over 2. The sum of its sides is AB times AC times BC, and if we divide by 2, we get the semi-perimeter, that is 9.59. So actually, here I found out that the radius of the circle that is described by triangle ABC equals to the area of triangle ABC over the semi-perimeter of triangle ABC. The area of triangle ABC equals to 2.366 square units, and the semi-perimeter of triangle ABC is 3.59 units. When we divide these two numbers by each other, we get that the radius of this circle that is described by triangle ABC equals to 0.658 units. We finished with the first method, then I presented to you the second method. In the second method, We use, in the second method, use two rules. Rule number one, that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. And we also have rule number two, that the lengths of two tangents from a common external point to a circle are equal. Okay? And actually, here, according to the rule number one and rule number two, we proved that the green triangle is congruent to the orange triangle according to side rule. Here, the yellow triangle is congruent to the pink triangle according to side rule. Okay? From the fact that those two triangles congruent to each other, we conclude that those two angles are equal to each other. But we know that the sum of those two angles is 60 degrees, and they are equal to each other. Therefore, each angle must be equal to 30 degrees. The sum of those two angles that are also equal to each other is 75. Therefore, and they are equal to each other. Therefore, each angle must be equal to 37.5 degrees. We use this here tangent theta in order to find out the value of BD. We use tangent 37.5 degrees in order to find out the length of DC. And we know that the sum BC plus DC equals to BD plus DC equals to BC, that is 2 units. Okay, here we have the value, we know that BC equals to BD plus DC. We already found out the value of BD, this is the value of BD, this is the value of DC. And we know that BC equals to 2 units, so we have only one variable that is missing, that is R. We solved this special simple equation and found out that R equals to 0.6589 units. So I finished the first question. Then I presented to you the second question, and we solved the second question in two different methods. According to actually we have here rectangle ABCD. Inside rectangle ABCD we have a circle that is inscribed by the rectangle, and we have to find out the area of rectangle ABCD. So here we use rule number one, that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. And we also know that the sum of the angles in any quadrilateral is equal to 360 degrees. And here we also use rule number four, that when you draw perpendicular from the center of the circle to any chord that is inside the circle, the perpendicular bisects the chord. So here the perpendicular OM bisects chord PS into two equal parts. The chord PS is 3, so each part will be equal to 3 units. Again, PS equals to 6 units, therefore each part must be equal to 3 units. And then we also used rule number 8, that parallel alternating angles between parallel lines are equal to each other. We know that OP is parallel to QL, therefore those two angles that are defined as alternating angles are equal to each other. So if one angle is theta, the other angle must be also equal to theta. Then I found out the value of cosine theta in this right green triangle. I found out the value of cosine theta in the big right triangle. And we created equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. And in this way, we actually here cosine theta according to equation number 1, cosine equals to cosine theta according to equation number 2. So this is equation number 3. Of course, multiply the equation number 3, we found out that the area of rectangle ABCD equals to 66 square units. Then I presented to you the second method to find out the area of rectangle ABCD. According to the second method, we use here actually the rule that states that any perpendicular angle that rests on the diameter of the circle is equal to 90 degrees. So therefore, peripheral angle HSP, this peripheral angle that rests on the diameter HP of the circle, must be equal to 90 degrees. And then we actually proved that the green small right angle HSP is similar to the big right angle QFP according to angle similarity rule. Those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. Those two angles are both equal to 90 degrees, therefore they are equal to each other. And this angle is a common angle that belongs to both angles, therefore this angle equals to itself. And here we have, therefore we prove that the two triangles are similar to each other, and from the fact that they are similar to each other, we conclude that FP over SP equals to QP over HP. FP is A, SP is 6, QP is M, and HP is B. Here we first multiply the equation number 1, and we found out that AB, that is the area of rectangle ABCD, equals to 66 square units. So in both methods, we found out that the area of this rectangle ABCD is equal to 66 square units. And in the first question, we found out in both methods that the radius of the circle that is inscribed by triangle ABCD, it is equal to 0.6589 units in both methods. Okay? Thank you very much.